All right. Whew. Should probably there we go. Okay. Welcome back to class. Happy Thursday. Does anybody remember what we talked about last time? Good. Ah, trash. Oops, that was the wrong one. Good old Laplace. Okay, and we also discussed the idea of a transfer function. Okay, and what a transfer function is once again, it's the input goes into some kind of a control, it's modified, and then goes to output. And the control, if we were to write a relationship for this, the control is equal to the output divided by the input, and then this control then is the transfer function. It is the relationship between the input and the output. Now the transfer function itself requires a Laplace transform. So the equation is g of s is equal to, I guess we'll do x and y, where y is your output. So it's the Laplace transform of y of t, which is the output, divided by the Laplace transform of x of t, which is your input. Okay, and then this is your transfer function. So, transfer functions are fun because they take a lot of math to develop, but this is ultimately what this is. It gives us the ability to define inputs and outputs linearly. Okay? When we had the equation that was what I of s is equal to d squared vc over dt squared plus I think it was zeta omega n dvc over dt plus omega n squared vc. We had a relationship like this where vc is your input, your output, and is is your input. When we have a relationship like that, it's not really easy to develop what this transfer function is. If we knew what the transfer function is, we could take this system, plug it in somewhere, multiply it by whatever the Laplace transform of the input is, and get the output right away. It wouldn't be that hard. So, for this type of a system, the transfer function is going to end up being, we're going to take the Laplace transform of the output, which is over here, and the input, which is over here, and we just have to divide them by each other. Okay, so if we're dealing with a system where f is equal to mx double dot plus cx dot plus kx. This is the input. This is the output, because every one of these has an x in it, where x is the output here. So we take the Laplace transform of both sides, and we divide this side by this side. That'll give us what our transfer function is. And that'll give us some insight as to, it'll give us some insight as to how we can learn more about this system. So, okay, so we've got these two. These are examples. We can also talk about heat transfer. We can also talk about other types of systems. Okay, so with these two, let's go ahead and look at Laplace transforms. Now, Brandon, you gave us you sent me a file for a Laplace transform table, and I haven't had a chance to upload it to the drive, but I'm planning on it. But apparently he got that from the math department, so totally going to use that in this class. Where is that? This has a lot of the functions that are typically used. So here, with f double prime x of t, which is what this is, the Laplace transform of x double prime is equal to, oh, this is x of t, is equal to, am I still visible on the camera? Oh, I am, yes. Big X of s minus s x at 0 minus x prime at 0. I think that was it. Yes, that's it. Okay, so this is one Laplace term. We've got another one, which is x prime of t is equal to x of s minus s. Make sure that I'm doing this right. I don't have all these memorized. Yep, this is just minus x 0 and then of course we've got the Laplace transform of x of t is just equal to x as a function of s. Okay, so those are the three variables that we're dealing with right now, and we see that this shows up here and here. So the general equation that we get coming out of this is if we take the Laplace transform of f, which this should have been a small f, but whatever, f of s, nope, trying that again. Laplace transform of f of t, which that's the force function, is equal to the Laplace transform of mx double prime plus cx prime plus kx. Okay? So we have these two equivalencies, and then all we do is we take the Laplace transform of each individual component. The Laplace transform of a function is just the uppercase of that function in terms of s. So this becomes capital F of s is equal to, we can break each one of these functions down. This becomes m multiplied by this value, which is capital X of s minus s x 0 minus x prime at 0 plus c times this value, x of s minus x0 plus k times this value, which is just x of s. Okay, so what we're doing right now is we're developing a cogent system. We have 3 x of s's here in our system. All 3 of those can be added together. We have an sx0, we have just a plain x0, we have an x prime of 0. So we'll go ahead and combine all of our like terms, just to simplify this a little bit. So we have f of s is equal to, I'm going to combine all of my x of s terms. So that's m plus c plus k. And then all of my non-x of s terms. So that's going to be plus, minus m s x 0 minus c x 0 minus x prime 0. Okay, so here's the terms multiplied by x. Here's the terms that are not multiplied by x. They're multiplied by, these are going to be constants. X at 0 is, if you look at your time function, if this is x versus time, your x of 0 value is going to be whatever's happening on the graph right at the start. So that's x of 0. Your x prime of 0, same thing. Or x dot at 0 is going to look something, you just take it at this value, this is x prime at 0. So this is a single number. This is a single number, this is a single number, this is a single number. This is a function, this is a function, all 3 of these are constants. Hopefully I have thoroughly confused you by this point. Just doing some kind of mathematical transformation here. Okay, now what we're going to be looking for ultimately is we know g of s is equal to your output divided by your input. This is our output, this is our input. So the transfer function that we're going to end up having to create here, this is the input, this is the output, is we're going to have to clean up both sides. And we're going to have to get x of s divided by f of s. Okay. So we're looking for f of s in terms of, we're looking at x of s divided by f of s. So if we take this equation right here and we divide both sides by f of s, what do we get? We get 1 is equal to x of s divided by f of s times m plus c plus k minus 1 over f of s times msx0 plus cx0 plus x prime at 0. Okay? Well, this right here is our transfer function. And this is what we're trying to solve for. So I'm going to go ahead and replace this with g of s. M plus c plus k minus 1 over f of s times msx0 plus cx0 plus x prime or x dot 0. Now we need to solve in terms of this. So we'll move this to the other side, and then we'll divide by that. And we'll have g of s. So moving this to the other side, we get, actually I'm going to take this, I'm going to flip it. So now we have g of s times m plus c plus k is equal to 1 plus 1 over f of s times msx0 plus cx0 plus x prime 0. Okay, now if we divide both sides by m plus c plus k, what we end up with is the following. G of s is equal to f of s. What I'm going to do is I'm going to take 1 and I'm going to replace this with f of s divided by f of s so that we can combine these terms into one giant quotient. So this becomes f of s plus msx0 plus cx0 plus x prime 0 divided by f of s times m plus c plus k. And this is our transfer function now. Okay? All right. So, does this kind of make sense? Sounds like fun. All we're doing is we're trying to come up with the relationship between x and f in the Laplace transform area so that we know what this is. This is a linear relationship where if we were to multiply this formula by f of s, by the transfer function of f of s, it would always equal x of s. And that allows us to create systems where we now have transfer functions multiplied by each other. Okay? It's the whole goal of this. And you can take both top and bottom from this. You can do the inverse Laplace transform and figure out what each of these components are. M plus c plus k is a constant. M is a constant. C is a constant. x0 is a constant. And x prime is a constant. So really this just ends up with is, if we say, let's say C1 is equal to Cx0 plus x prime 0. And we'll make C2 is equal to mx0. And we'll say C3 is equal to m plus c plus k. So all we're doing is we're just going to clean this up a little bit. Then this transfer function is now equal to f of s plus c2s plus c1 divided by c3 times f of s, where c1, c2, and c3 are all constants. Okay? This is solvable if we know what f of s is. Okay? Let's say that the forcing function here, I'm going to go ahead and erase this part of the board. Let's say that our forcing function is just a constant force. Constant force is pretty simple to deal with. So if f of t is equal to, I don't know, maybe mg. Maybe this is a suspension system and it's just the weight of the vehicle. Okay? Then f of s is equal to the Laplace transform of f of t, which is equal to the Laplace transform of mg, which mg is a constant. So if we go back to the table that Brandon so nicely provided, the Laplace transform of a constant is equal to 1 over s. So this is equal to mg over s. Okay, we can now plug this in for f of s here and here. And what we get is our g of s is equal to mg over s plus c2s plus c1 divided by c3 times mg over s. Okay, that's fun. In a quotient like this, we generally don't like having quotients inside of it. So we'll multiply top and bottom by s. So this is going to be equal to mg plus c2s squared plus c1s divided by c3 mg, which all of those are a constant. So that's interesting. Our transfer function comes out really nicely. So cleaning this up just a little bit further, this is now equal to 1 over c3 mg, which those are again constants, times c2s squared plus c1s plus mg. This is a quadratic equation. We can find the roots to this. So that's nice. If you want to find the roots to this, the roots for this equation are, just using the quadratic equation, negative b plus or minus square root of b squared minus 4ac all over 2a. So here our b is c1. So this equals negative c1 plus or minus square root c1 squared minus 4 c2 mg divided by 2 c2. Okay, so as much fun as that is, yeah, that was a lot of fun. From this now, we can simplify it further. I'm just playing with math at this point. G of s is equal to 1 over c3 mg times the value s plus s plus negative c1 plus the square root of c1 squared minus 4c2 mg divided by 2c2 times s plus negative c1 minus square root c1 squared minus 4c2 mg. I'm writing way off the screen at this point. Divided by 2c2. I know I am. So just playing with math. That's a solvable function. I am way off the screen. I don't want to rewrite that. That was a giant equation. I'll move the camera. So, giant equation. But now what we have here is taking the inverse Laplace transform of this would be very simple. The reason why we play around with math and Laplace transforms is that's something easy to solve. There are values for that in the table. So really when it comes down to doing transfer functions, the reason why we do Laplace transforms, even though it is a little bit weird, is that you have the ability to jump in here and really rearrange all of these variables to come up with something tangible. We can get a value that is a function of time out of this just by inverting it. Okay? And it is solvable that way. So, this is one method of solving differential equations. This isn't the most enjoyable thing that we're going to be talking about in this class, but it is really important to understand as far as control system theory goes. So, yes, I know this is a little overwhelming. That's okay. Don't be scared of math. Math is your friend. All right, any questions? Okay, we're going to go ahead and break into group time, so I'm going to end the live stream, and then